Hello again. Welcome to Lesson 30, Pipe Networks and Pumps. Our objectives today are listed. There are quite a few, as you see, so make sure you take a moment to review them. The first thing we're going to talk about today is pipe networks. Pipe networks are designed to deliver required flow rate or to deliver a desired pressure. And there are different types that we will discuss. The first type is in series, and this is where the conservation of mass is satisfied through the system. And we can have flow moving through a bit of pipe where we have a reduction in the pipe. Conservation of mass is going to be satisfied. We still have steady flow, but the area is different, so the velocity in the pipe upstream will be higher. The other type is parallel. And this is the conservation of mass applies at each junction. Head loss between the two junctions must be the same for both paths. So here we have it. Parallel conservation of mass applies at each junction. The head loss between the two junctions must be the same for all paths. Now, that's if we have multiple lines. Now, what does that actually show? Well, let's go into parallel networks a little more so. And I'm going to recreate figure 1435 in the text. So for our parallel pipes, if we have, and again, this is figure 1435. If we have two lines, point A is the junction prior to split, and point B is where they recombine. The lines are going to have line 1 and line 2, path 1, path 2, are going to have separate friction factor, different lengths, different diameters through them. The pressure, there's going to be a pressure associated with A and a pressure associated with B. The pressure at B, because of the losses, pressure drop, must be less than pressure A. In order for these two lines to come back together and actually flow in this direction without this being a total branched flow, if this is not pressurized, the head loss for 1 has to equal the head loss for 2. So the losses through 1 have to equal the losses through 2. And on a similar note, my volumetric flow rate at point A has to equal the volumetric flow rate for path 1 plus the volumetric flow rate for path 2 because of continuity. And this goes back to incompressible, sorry, is equal to volumetric flow rate B. So this is kind of what has to happen for parallel pipes. If this situation does not exist, then you'll just have flow going through line 1, and this flow 2 will be static or just stagnant. It will be like one of the offshoots on the Hudson, where this is the main river and this is a marshland, if you will. So, a bad analogy, I agree. But if you don't have the same pressure drop through the lines, they're not going to recombine and move forward together. Now, what else can we use this for? Well, we can get parallel flow ratios, get a velocity ratio, get a volumetric flow ratio, and let's do that next. So if head loss 1 equals head loss 2, that means my friction factor 1 times my length 1 over diameter 1 times velocity 1 squared over 2 times g is equal to the same for state 2. Diameter 2, velocity 2 squared over 2 times acceleration of gravity. Well, I can divide this through and come up with a velocity ratio where I've isolated velocity 1 divided by velocity 2, get a ratio of the velocities, and it's equal to friction factor 2 divided by friction factor 1, length 2 divided by length 1, and diameter 1 divided by diameter 2, because those are in the denominators, all raised to the 1/2 power. Similarly, I can get a volumetric flow rate ratio. And this is recognizing that area is my difference here for volumetric flow rate, so it's going to be another diameter squared, or it's going to be a diameter squared. So V dot 1 divided by V dot 2, my volumetric flow rate, is going to be equal to diameter 1 squared over diameter 2 squared times the remainder within, length 2, length 1, diameter 1 over diameter 2, raised to the 1/2. Okay, so why do we use this? Well, we want the head loss has to be constant because we said the pressure drop is constant. These could be nice ratios, velocity 1 compared to velocity 2. It's all dimensionless at that point, and so we can pull out what our friction factor would need to be, or what have you, if we know the ratio, or we're designing towards a ratio. Next, we're going to talk about pumps. Pumps require a work input to increase pressure head, and there are different types of pumps. A couple that we'll talk about are axial and centrifugal. And they have various different power inputs. We could have a shaft, a turbine turning my pump shaft, as we saw in the power plant, or it could have an electric motor. So those are all what turns the shaft, which creates my axial pump or my centrifugal pump. Starting off with the conservation of energy, I'm going to do a quick analysis of the pump head through, or between two free surfaces. So my pressure head plus my velocity head for state 1 plus my elevation head plus my pump head is equal to pressure head for state 2, velocity head, elevation head, turbine head, head loss. Alright, if I have two free surfaces and I'm pumping in between, so basically I've got one free surface, another free surface up here, and I'm pumping water between the two. So my pump goes like this. I have an input, pump it up into my exit. Why would I do this? Well, at nighttime sometimes you want to store energy. So let's say we have wind power, and we have available energy at certain times, but not very predictable. So that wind power will turn, when it's on, will turn a pump, will power a shaft for a pump, and the water from low will be taken to high. This is basically storing energy, so if we have at some future point connect this to a hydroelectric, build it up, put it through a hydroelectric water turbine, or water turbine creating electricity, we now have energy, available energy, because of this stored potential. So that's one case when it would be important to do this. Alright, well, what can we cut out? If I'm going to free surface, my pressures are the same. Large reservoir assumption tells me that the velocities are the same. My height difference is definitely pertinent. I have no turbine, so now I'm left with my pump head is equal to Z2 minus Z1, my change in elevation, plus my head loss. Alright, and this is equation 14-47. And again, always start with the mechanical energy equation and work this through. If you just go reaching for equations, you're going to end up hurting yourself come test time. Alright, well, now that we've discussed the pump head, we can get the pump power. So if I want the shaft pump power, if I have a shaft driven pump, this is equal to the power of the pump by shaft is equal to my mass flow rate times my acceleration due to gravity times my pump head divided by my pump efficiency. And I can write this, my mass flow rate, in terms of density, gravity, volumetric flow rate, pump head, and efficiency. And this is 1448. Okay. So that is how I would get the power that I am looking for the shaft power. Now my electric power, if I have an electric driven pump, I will have the efficiency of the motor. Electric pump power. So I get the same thing, but now I have an efficiency of the motor. And we see here this efficiency of the motor in addition. And that's equation 1448. Now my pump efficiency varies with my flow rate, or it can. And how can I predict my pump efficiency? Well, I have to go to the pump curve for my pump, and that's figure 1438. So I'm going to quickly resketch this, or sketch this on our tablet here, and discuss the key points on that. Okay, well here's our figure 1438. This curve here is my pump head utilized. So we call that pump head, comma U. This is my system curve. And where these two intersect is my operating point. That's the best case operating point. And they depend on the flow rate. So as I increase the flow rate, the system curve goes up, the pump head curve goes down. So my head decreases with increasing flow rate. My pump efficiency is this green dashed line here, and that marries up with my pump head, because if there's no head, it's just free flowing. So that's my max flow rate with minimum head. My max head has zero flow rate. So that's called shut-off head, as your figure 1438 depicts. Alright. Now, what do I use this curve for? Well, that's a great question. Typically, it's squirreled away somewhere and you rarely look at it. So, let's actually figure out what it's for, so when you're in this case you might actually know what to do with it. The system curve is determined by need. So that's, what do I want out of my pump? What do I need out of my pump? The operating data the pump head, useful, and efficiency of the pump are provided by the manufacturer. So that's how I get my other line. Manufacturer, okay. And lastly, the operating point is where the system curves intersects my pump head curve. Okay, and lastly, one of the concerns in the design is putting saturated liquid at most into my pump. That is because pumps cavitate. Cavitation, this is section 9.4 in your text. If I have a pump where I put in at A and I take out B, if I know pressure B is greater than pressure A, that's definitely the case. If pressure A is less than pressure saturated, then the fluid will vaporize. So let me restate that. If pressure A, the pressure at point A, state A, is less than the saturation pressure for that temperature, the fluid is going to vaporize. It will turn to steam. This typically happens if you're trying to suck. If you have a negative head for the pump instead of a positive head going into the pump. So what you'll find is, if my pump is too high up and my reservoir is below, and my pump is trying to suck water or fluid out of my reservoir and then push it forward, there's a possibility, because the loss is in the line and the elevation difference, that this will drop the pressure prior to the pump at some point below the saturation, and I will start vaporizing my working fluid, which is normally water for us, and then my pump will be pumping vapor, which is very noisy and actually damages the pump quite considerably. So the concerns are that it's, well, cavitation bubbles. The bubbles caused by cavitation damage the pump, are noisy, and they cause an efficiency drop. How do you prevent it? Use the energy equation to ensure that my pressure at A is greater than my saturation pressure. So to avoid it, I'm going to use the energy equation to ensure the pressure at state A is greater than saturation. Okay. And there we are done with lesson 30. The next block is vapor compression refrigeration cycles. After this test, or after this class, we'll do a problem-solving lesson, double block, and then move into our WPR2. So, I wish you the best. If you got any questions, call your instructor, contact your instructor somehow. Otherwise, have a nice day.